everything. I said, sure, it would be great. And I said, well, and I thought about what I want to talk about. And then I said, well, what question would people like an answer? So, and one thing that I always see in the popular press, and when people say it, in the way they always say it, without actually explaining it, is that quantum mechanics and general relativity is not compatible. It's very hard to unify those two. So Michael started this introduction saying that, well, we have two shirts, quantum mechanics and GR. We want to make it, we want to put one equation on one shirt. So why is it so hard? Why is it so hard? So I said, well, let's talk about that. And of course, the first thing I do is I Google. Right? So that's what I do. Even we do it. Right? So we Google. I say, okay, well, is there like somebody ever say it and you just copy the talk? Well, turns out that I can't find anything. Right? So then I start to panic. I say, okay. So this talk, like I was obsessed with it for 3 weeks, and it's, I think at the end I like it, but it's sort of a little bit of an experimental talk. So hopefully you all like it. Right, so okay, so unification. So why should we care, right? So what do we mean by unification? Well, roughly speaking, we want to combine the rules of quantum mechanics and general relativity. It's not nice to have two shirts, right? You always want a favorite shirt, and you want all your equations to be on that favorite shirt. So two shirts, you can't have two different rules described in the same universe. So we know that somehow, they should be on the same shirt, and we should have the same set of equations, or at least some combined equations. So we want to combine those two equations, but there's an obstruction, right? There is an obstruction on why it's so hard to do that. And it turns out that as I was trying to understand this talk, and I was trying to understand it enough to give a talk on it, it does span everything we know about quantum mechanics, special relativity, and general relativity. And it has some like wonderful consequences of this that trying to understand this obstruction. So I want to give like in a sense a proper talk, quote unquote, right? So I set myself some rules, right? The two rules that I have is that I will try to be as accurate as possible. So, well, good luck, Eugene. And two is that if I gloss over things, if I cheat, if I say, this is too much to talk about, I don't have time, I will tell you, right? Maybe I'll tell you, like quickly, but I will tell you. So hopefully you'll be as accurate as possible. Right. So ingredients. So why to understand why is it so hard? We need there's some ingredients, and the four ingredients that really we need to understand this obstruction is this following. So one is quantum mechanics, rule number one. So we want to unify quantum mechanics and GR, so quantum mechanics have to come in somewhere. So the first rule that we need is the Heisenberg uncertainty principle. So you may or may not have heard of it, but I'll tell you what it is. And then two, in quantum mechanics, which is another like most words that people throw about, and it's actually quite true, which is that in quantum mechanics, everything that can happen has the chance of happening. Right? So that's rule number two that we need. And the third rule is the one equation that I allow myself to have in this talk, which is E equals mc squared, which everybody knows. Which in English is translated simply.
Pointing a different block.
Oh, so I need to. Is this a pointer?
Yeah.
This is a lightsaber. Right, here you go. So in words, right, it means energy is mass, right? So that's the ingredient, right? You can't give a talk on physics, even a talk like this, without using E equals mc squared, and we will use it. And finally, since we are trying to unify quantum mechanics and GR, I can't say general relativity, so I'm going to say GR, right? So you want to unify GR with quantum mechanics, then GR tells you, as Marika told you, that you can make black holes by putting a lot of stuff in a small space, right? So these are the four ingredients that we need. So how do they come in? So let's start. Right. So Heisenberg uncertainty. When I Google Heisenberg, I have 5 pages of Brian Preston, right? So he is Heisenberg now, Werner, sorry. So the popular version of Heisenberg uncertainty principle, which is you already probably heard before, is that you cannot simultaneously measure the momentum and position of a particle to arbitrary accuracy. So if you know the momentum of a particle is super accurate, then you actually don't know the position. Right? So that's what the Heisenberg uncertainty principle tells you. But that's the problem. popular version. So the last popular version, which I call the interest-free loan version of the Heisenberg uncertainty principle, and this is a real Heisenberg, is that, and this why we call it interest-free loan version is because you can borrow free energy from empty space as long as you pay it back within a short period of time. And furthermore, nobody's watching. So you can, right? And the more energy you borrow, like any bank, the more energy you borrow, the less time you can borrow it. But this is a great bank because you don't need to pay interest. So you just borrow as much as you want. If you borrow a lot, you have to pay back faster. That's it. No, they won't charge interest. Right. So this is what we're going to use. Right. This is the equation. This is the first element of the four ingredients that we're going to use. Right. So why do we need that? Let's just consider an electron. An electron, we all know what an electron is. It's here. It's moving from left to right. So this. It was orange on my screen, but it's not red here. So a red electron moving from left to right, here's an arrow, that's the direction of the move, can actually spontaneously emit a photon. Right? What it did is that the electron went to a bank and borrowed some energy and made a photon. Right? So that's why it can spontaneously emit a photon. It started with no photon, and suddenly you have extra photon flying out. And this is what's going to happen. This is the energy of the system. So you start with electron, there's some energy here. He borrows some energy, emit a photon, and there you are. So we borrow some energy to make a photon. But like we said, we need to pay it back. Right? So you can pay it back interest-free before anybody has a chance to watch it by absorbing it back. So you borrow some energy, you make a photon, and you absorb it back. And here we are. This is what's happening in the quantum world when nobody's watching, right? So, and this is basically the process which Marika talked about, when you say, there are virtual particles popping out in the vacuum. Basically, the vacuum borrows some energy, make two particles, and before you see it, they come in and annihilate. So you actually won't see that. Black holes change the story, of course, so, but we'll get there. All right, so there's a technical word for this, and I try to reduce the amount of technical word in this talk, but this is one thing that I think regularly will be able to understand, which is that this fluctuation of energy, this borrowing, is called quantum fluctuation because it's a quantum effect. And this photon, because you never actually see it, we call it a virtual particle. It's a virtual photon, a photon that exists virtually. And this loop here, every time you see a loop, it basically tells you that there's some quantum fluctuation because you borrow some energy and you pay it back. So it is a loop. Right? Every time you see a loop, think quantum fluctuation. Or if you are more, you want to think about borrowing and money and borrowing energy from free space. Okay, so, and as Heisenberg told you, the more energy you borrow, the less time you can borrow it. So here's two diagrams or two pictures of what happened. You can think of it in a diagram, or you can think of just actually electron moving from left to right. Right, so a bigger loop means that you borrow less energy. And a smaller loop means that you borrow more energy. Why? Because if you borrow less energy, the photon has more time to exist before you pay it back. So it has more time to move. So it moves a little bit further before it gets absorbed. And if you borrow a lot more energy, you have to pay it back a lot more quicker. So you have less time to move, so it moves a lot less, and then so the loop's a little bit smaller. So every time you see a big loop, it means that you borrow less energy. You see a small loop, you borrow a lot more energy. So this is just a way for you to remember how to think about these things. Okay, so quantum mechanics rule number 2. Everything can happen, will happen. Right? So if this quantum fluctuation can happen with some energy, it can happen in all possible energy. So it can including infinite energy. So here's our possibility. I just draw 3, but you can imagine a million or infinite number of them. So here's an electron borrowing some energy to make a photon and absorbing it back, an electron borrowing a little bit more energy and absorbing back, an electron borrowing a lot of energy, make a photon and absorbing it back. So if you like going right, you can imagine there are smaller and smaller and smaller loops, there are more and more and more energy. Furthermore, because anything can happen, everything can happen, that can happen, will happen, you can take 2 loans, right? You can take a loan to buy a car and take a loan to buy a house. So you borrow some photon, the most energy to make a photon, and they say, okay, I haven't paid back this loan yet, but I can go to another bank and borrow some more energy. But here we are. So you have 2 loops instead of 1 loop. So electrons is like real life. Right? I'm just stuck until I'm dead with that. Credit card, blah blah blah. All right. Okay. So the next 2 diagrams I'm going to show you is actually very complicated. I just warn you and say don't worry about it. I'm just showing it just to show that because of this possibility of borrowing as much as you want, you can imagine. Quantum mechanics tell you there's many different ways of electron can move from left to right. Right, here are two like crazier diagrams. This is don't worry about it. It's designed. I designed to be complicated just because I want to show that it is complicated. But you can imagine that a lot of different infinite number of combinations that you can come up with. But this and quantum mechanics tells you if it can happen, it will happen, or it may happen. Okay, so reality is democratic. So from all these possibilities, which one actually happened? Which one? Well, the answer is all of them at once. So what does that mean? It means that there's a fundamental rule of quantum mechanics that tells you that the probability of any process is the sum over all the possibilities. Now this is a rule, so in other words, all the possibilities just now that I showed you, if you want to calculate the probability of some process, you need to take all the possibilities and add them all up. Now you can ask, well, where does it come from? Why is this true? The answer is that I don't know, right? Nobody knows. This is just the way it is. You know what I mean? This is the rule of quantum mechanics that we come up with that actually fits the experiments that we make. So we actually don't have any good idea about why this is true. This is just the way it is. So again, this is like a mathematical axiom, right? Like more like a physical axiom. This is a true fact that we don't have an explanation. All right, here we are. So now I'm going to use the fundamental rule of quantum mechanics to calculate what is the probability of an electron moving from left to right. So what do? I just add them all up. So here you go. Here's the electron. I say the probability of electron moving from left to right is when it borrows no money, it borrows some money, it borrows some other a lot more money, plus a lot more money. So you can imagine you can keep adding them up with all the possibilities and you add them up. Some crazier possibility, and all the possible combination of energies. Infinite number of them. All possible size of the loops, all possible different diagrams that you can think about. And then you sum them all up. Either you buy a very good computer, you hire a very smart graduate student, or you do it yourself. You just do it and get what you get. That's the question. All right. So for any given theory, when there are two possibilities when you sum up an infinite number of terms. First, you get a finite number. Two, you get infinity, right? So again, this is like 50-50, right? You either get a finite number or infinity. Okay, this is a joke. So, this is kind of a joke, really. It's not really totally a joke. Why is not? So if you get a finite number, you add up all this infinite number of terms, and you get a finite number, congratulations. Why? Because your theory is complete. What does that mean? It means that you have a theory, you apply the rules of quantum mechanics, you add them all up, you get a number. Why a finite number is important? Because you can pass it on to your experimentalist friends to check whether or not your theory is right or wrong. If you give them 5, they say, okay, go look for 5. If it's 5, then awesome. If it's 6, then okay, go back and do something else, right? So it's important to get a finite number. So this is why, so this is possibility 1. So quantum electrodynamics, there's a complicated name, but it's basically a quantum theory of photons and electrons, like the one I explained to you, like all these things. When you do all this summing up, like I just told you to, you actually do get a finite number. So if you like, quantum electrodynamics is a complete theory, it's a theory that's done. And you can actually check it, you pass it on to an experimentalist friend, they go do the experiments and they check it, and it's tested to 1 part in 10 billion, so it's actually super duper accurate. It's like our most successful and predictive theory. Yay, right? So this is like the archetypical perfect theory you can think about. It's perfect. You can test it. You can test it. It's super accurate. It gives you a finite number when you compute it. It's great. All right. So if you get infinity, then you're kind of screwed, right? So because if you get infinity, you give it to your experimentalist friend. They say, get out of the room, right? So because you can't test for infinity. You can't go and say, oh, I want you to make this measurement and get infinity. They say, what the hell are you talking about? Right? So in other words, your theory is not predictive. You're not predicting anything. You get infinity. It doesn't make any sense. So does this happen? It turns out it actually happens a lot in physics. That's why we get paid a big bucks, right? So it happens all the time. And here's an example, right? So example again the standard example that you use is radiative decay. Right? So a carbon-14 molecule or atom can decay into a nitrogen-14 by emitting electrons. So if you want the neutrons of this carbon-14 can decay into a proton, making a nitrogen-14 and emitting electron. So this happens. People seen it since like the early 20th century. We know this process happens. if you stand close to it, it will kill you. So okay, well, when death is involved, right, people care about why this is happening. Right? So we want a theory to explain this thing. So why does this thing happen? So a very clever guy called Enrico Fermi came out with a theory of radiative decay. And here's what he says. So here's how a neutron can decay into a proton and vice versa. Don't worry too much about that, it's just behave. So here's what he says. I have a neutron, my neutron can evolve and get hit by a neutrino, and neutrino and neutron is going to combine, make some crazy stuff here, and then out come a proton and electron. Crazy, but actually it works. Right, so he says that, again, and repeat, that a neutron and neutrino can combine to make a proton and an electron. Now, I've cheated here a little bit. The real diagram for this process is actually, if you look from this corner to that corner. If you like a neutron, it's actually decaying to a proton, and neutrino and electron. But that's, again, it's details. Don't worry too much about it. So now, Fermi is a very clever guy, right? So he came up with this theory, and he did all the calculation. It was great. This theory was awesome. If you ignore quantum fluctuations, if you just forget about the quantum mechanics that I told you about, this theory is actually super good up to a certain limit of energy. So this theory sort of works for the cases that he can build experiments for, but when he tried to build experiments with higher energies, where he collide a neutron to a neutrino at higher energy, it sort of starts to fail. But it all works. So, you know, so it's good, right? It's good that it works some of the time, not all the time, just like most things. Okay. So now let's just now apply quantum mechanics. Let's just now see why it works. Right? So if you take this theory and say, wow, okay, now let's imagine that quantum mechanics now comes in, you can have all this quantum fluctuation, you can start borrowing energy to make new particles. So let's forget about the particle type and just look at this diagram. There's two particles coming in, two particles going out. You could borrow some energy here to make two other particles that that travel in space, and then eventually you have to pay it back. So you pay it back and then you make two other particles. So you remember, a loop means some quantum fluctuation. A big loop means a little bit of energy. A smaller loop means a lot more energy. Even a smaller loop means a lot more energy. Right? So you're borrowing some energy, you're borrowing a lot more energy, and you're borrowing a lot more energy. And again, you can have all these possible crazy combinations. I won't talk about it, but just imagine there's, again, infinite number of diagrams you can do. So you can compute this, you sum them all up, and you get infinity. Right? So this is a theory that is not, you can't say, okay, that is not, you can't say, Enrico Fermi will come and kill me, right? So it's actually not a bad, it's a theory that is not predictive when you try to apply quantum mechanics to it. So the question is, what now? What do we do now? Well, all is not lost. Well, again, I say, if you ignore quantum fluctuation, the theory is actually very good and predictive. And it's actually, so there must be something right about it. It's not all wrong. Maybe it's just not wrong, maybe it's just like incomplete, maybe you're missing something. So how do we know? How do we guess at what's missing? So what are the rules that we have to tell us what's missing? So in other words, furthermore, like, radiation decay occurs. Right? You stand next to a radioactive object and you die, so it actually happens. So what's missing in our theories? How do we tell? So to understand how we fix the theory, let's go back to the electron and virtual photon. So again, this is electron borrowing some energy, emit a photon, come back and absorb it. Here we go. So this is, we have seen this before. So but suppose there's another electron nearby. Right? So here's electron 1. Electron 1 borrows some energy, emit a virtual photon. And electron 2 just happens to be around the area. Now instead of like the photon getting absorbed by electron 1, the electron 2 can actually absorb the photon because it's close enough. The photon decided, you know what, I don't want to get reabsorbed by electron 1. I'm going to get absorbed by electron 2 instead. This can happen. So if you like, I'm going to move on to the next slide now, but this is so amazing that I have to spend maybe a minute on it, which is that this thing that I just showed you is actually the origin of forces. You might wonder that, okay, well, I have what is electromagnetic force, right? What is magnetism? What attracts two magnets? What is, in fact, this idea you can think about in terms of gravity. So what is a gravitational force? So you like, this is exactly what's going on when two electrons repel each other. Because two electrons have negative charges, how do they repel each other? This is the process. They repel each other by exchanging a virtual photon, right? So, but this is the story of another talk. But we're going to use this idea that an electron a particle can emit a virtual particle to be absorbed by some other particle. How we're going to fix the theory that was broken, as I told you just now. Okay, so how do we fix this theory? Let's suppose something similar happened in Fermi theory. told you that was broken. So now instead of a neutron and a neutrino coming in and do some crazy stuff, to come out with a proton and electron. Suppose this is what happened. This is actually what happened. Let's just, this idea, takes like many years of people to figure it out. So I'm going to tell you what the idea is. The idea is the following. This neutrino is going to come along, and it's going to borrow some energy. It's going to emit some crazy new virtual particle that we're going to call W, whatever it is, or whatever it is. So it's a new virtual particle. So this particle is a virtual particle. You cannot see it because it's just borrowed money. And after it emitted, it becomes an electron. Now, I didn't tell you why a neutrino can become an electron by emitting a W particle. I can tell you, but it would take too long. So let's just, something that you have to believe. I'm just going to, this is where I gloss over stuff, right? So this is where I'm glossing over stuff. So this particle, instead of being reabsorbed by this electron, it gets absorbed by a neutron that's floating around instead. So this neutron will absorb the W particle, and it's going to become a proton. Again, why does it become a proton? It's glossing over. Sorry about that. Okay. So suppose this happens. I'm not saying this actually happened. I'm just saying let's suppose this happened. Because quantum mechanics tells you that this may happen, right? Neutrino can borrow some energy, can make some crazy particle, can be absorbed by neutrons. So let's just take this and run and see what happens. So what particle is this? So now we have this special ingredient on top, which is special relativity, which tells that energy is equals mass. Right? So now you have this particle here, W, which is some particle with some mass. So if you want to make a particle of some mass W, you need to borrow energy from free space. You need to borrow energy from space. And how much do you want to borrow? Well, if you borrow sufficient energy, if let's just say that this particle W has mass m, if you can borrow enough energy from space to actually satisfy this equation, then you can make a particle of mass m, which is W. Remember that in quantum mechanics, anything that can happen will happen. So if this particle exists, you can borrow some energy from free space enough to be able to make this new particle. So if W exists, for the moment we don't know if W exists or not, it will pop into virtual existence. So let's just take a step back and remember what Fermi has to do. Fermi knew neutrino exists, he knew electron exists, he knew neutron exists, he knew proton exists. He doesn't know W exists. Why does he know W exists? Maybe we haven't built enough instrument, a powerful enough instrument to make it. So it's all he has is neutron, neutrino, proton, and electron. But if, let's just say, suppose that this particle exists, then this thing can happen. It turns out that if you add W and Z and something that you might know, the Higgs H. Right, so if you add a W particle, a Z particle, just the same way that I told you, instead of W, let's replace with Z, and instead of Z, replace with the Higgs, and recalculate everything. If you just add this ingredient into your incomplete theory, it turns out that the infinities disappear. Your theory is now complete. So now your theory is now predictive. You can go and give it to your experimentalist friend, and they can go and try to observe whether or not your theory is wrong. Now, at this moment, the theory is just a theory. Nobody has checked it. So, but these particles are very massive. So Higgs particle is 175 protons. And then that's the reason why this is massive, and I'll tell you a bit later. So this theory turns out that Z and W is actually named, and W is actually not whatever, I just make it up. Z and W were discovered by the super proton synchrotron particle collider at CERN, which this is actually the precursor of the Higgs, the Large Hadron Collider. Right? We all know that Higgs was discovered a couple of years ago, and this is the canonical picture of Higgs, of the CMS detector in the LHC. So this theory, which is now complete because you can compute them, you get finite numbers, is actually called electroweak interaction, and it's incredibly highly successful and predictive. Right? Many prizes have been given to coming from quantum fluctuations to this. And I actually have a slide with all these names, and it turns out that all it's kind of boring, so you just say white faces, and so it's kind of okay. So here's guys faces this. So here's the powerful principle, right? Here's the powerful principle that we have as physicists, which is if you invent a theory and make something up, check, apply the rules of quantum mechanics. Is the theory infinite? If it's no, great, theory is complete. Go pass it to your experimentalist friend. Go check it. If it's correct, go collect the Nobel Prize. This is exactly what happened like 3-4 times. I'm not kidding. Right? Now, if it's no, it's wrong, then I want to go back and invent a new theory. Right? And this is where I spend most of my time. So I'm never here. Okay, so that's the standard. That's when you read popular science book that they do this rule. What they don't do is this rule, which is that it's infinite. Most of the time it's infinite. Then okay, well, what do? You add particles of big mass to the theory, and then you go back and calculate again. If it's still complete, yes, great, you check it. If it's no, then go add more mass. This is really, if you want to summarize the life of a particle physicist, this is really all right. But this is actually a very powerful principle, because even though when your theory is not predictive, there's a prescription on how to fix it. And how to fix it is to add more particles, with big mass to the theory. And why? Because we know that to make particles of very big mass, if it's small mass, we will have seen it. So anything missing must be something in the big mass, right? So because you don't have enough powerful enough function to actually see it. So this is actually this is great. I love this formula. All right. Okay. So if you add W and Z and Higgs to the Fermi theory, it turns out that, of course, as I said, adding particles to the Fermi theory is not a unique way to fix the theory, but it is a way. And when people discover W and Z in the magnetic tree, we become super confident that we're going to discover the Higgs. Why? Because the Higgs doesn't exist on its own. It exists as part of this trifecta of particles that would fix the Fermi theory. So when there's a quote by, I think it was Steven Weinberg, that says that we're confident to discover the Higgs because we already discovered 2/3 of it, which is W and Z. So in a way, that's why we're so confident. That's why all the newspapers are gearing up to discover the Higgs. And if you really discover the Higgs, it's completely crazy. So this is the reason. Okay, so all about particle physics. Now this is the talk about GR. Right? So what about GR? What do you do? So our goal is to unify quantum mechanics with GR. So in other words, GR equations must obey quantum mechanics for them to unify. So let's just apply the rules of quantum mechanics with GR and see what happens. So a traveling gravitational wave, we can always call it a graviton. It's just like an electromagnetic wave, which is light. We can call it a photon. So you can call a traveling gravitational wave to be a graviton. You think of them as just a gravity particle. We can do that. Going from left to right, here we are. Again, you can, since you're applying rules of quantum mechanics now, you can apply rules of quantum mechanics and say, okay, allow virtual gravitons to pop in and out at different energies, borrow lots of energy, borrow some energy to make some graviton, absorb it back, borrow a little bit more energy, so a smaller loop, borrow a lot more energy, it's a much smaller loop. And again, you have other more complicated possibilities that can happen. Quantum mechanics tells you they have a chance of happening, so you can compute them. So and you know the trick, right? So quantum mechanics tells us to sum them all up, right? So this plus this plus this plus this plus this and all the possible combinations, and you can get them back. It's infinite, right? So GR breaks somewhere. Right, but we know that GR obviously works at some level. It's just that the Fermi theory obviously works at some level. So we know it works. So maybe it's just incomplete. But we know what we should do when we have incomplete theory, right? Add mass, add stuff. It's just like your soup is not good enough, add stuff. Well, at least that's how my cooking goes. So you want to fix GR. So let's just try to fix GR by adding species of gravity of massive particles at some high energies like we previously did. So suppose now instead of W, let's get some new virtual particle called P or whatever. And the mass of this hypothetical particle P can be estimated by combining all the physics that we add in, which is quantum mechanics, special relativity, and general relativity. So unfortunately, I only have one equation. I can't show you the beautiful equation that you derive this, but you can imagine that P is just some combination of all the numbers that define this tree theory. And once you've done that, you find that this mass is ginormous. It's super big. Right? So this P particle is 10 billion photons. It's a big math, right? I spent maybe 10 minutes doing this and I gave up. So quite a lot of particles. To make a virtual particle of this mass try to fix GR, you need a huge quantum fluctuation of energy. You need to borrow a lot of money. It's like trying to buy a Buckingham Palace. You have to go to a really crazy bank. So okay, right. So now the last ingredient on top is GR. And GR basically you can reduce it in 3 words, right? Mass, curve, space. That's GR. So if you put a lot of mass in a small area, like Marika told you, the space will curve so much that it becomes a black hole. Now it's can see what's going on, right? The amount of quantum fluctuation, the amount of energy you need to borrow to make this particle is exactly the amount you need to form a black hole. And if you try to save GR from these infinities that you're calculating using quantum mechanics, you borrow all this energy from space, and it turns out it's so big you'll make a black hole. But you know what's hiding inside a black hole? Hiding inside a black hole is a singularity. A singularity is another word for an infinity. So this is why it breaks down. This is where it fails. This is like you're almost there and go. Damn. So you actually end up with infinity. So you didn't solve the problem. Your theory becomes against unpredicted. And this is, if you like, you can see that I put all the ingredients in, and you are almost driven by all the ingredients you put in to this final conclusion. So, and if you like, you can leave now. But okay. So here's what like a picture going on. Like you try to do some quantum fluctuation or particle appear, poof, a black hole appears in space. But we know black holes exist. So why is it so bad? Well, I mean, black holes exist on its own if you think in terms of just GR. And if you worry about the singularities in a black hole, we don't worry about it. Why? Because it's hidden inside the event horizon. You never can see a black hole singularity. It's hidden. If you can go in and see a singularity, you can never go out because the horizon blocks you. You cannot escape the horizon. But our goal here is not to worry about whether black holes exist or not. It's to try to say, can we unify quantum mechanics in GR? Can we make computation when we put quantum mechanics in the GR? And the answer is no, because we get infinity. It's not predicted. So when you try to combine, basically this is what I just said. When you try to combine the rules, we get a non-predictive theory. And it's sort of hard to unify quantum mechanics and GR. Why? Because all these three, one of them must be wrong somehow. If you want them to fix it, all the theory, the rules of this tree theory, which have tested well, super tested experimentally, must be wrong somewhere. But they're so well tested experimentally, it's hard to you sort of working in the scripture. You're not quite sure what to do, what to change. And this is why it makes this job so hard. Again, they pay really well. To try to unify quantum mechanics and GR. Right, so it's one of those things, right? Then what is your party piece? When you go to a party and people, well, these parties I go to, people ask you this question, hey, so why is it so hard to unify quantum mechanics and GR? Right? And this is a thing that you can use, right? And then you say, okay, because quantum mechanics says that you can borrow so much free energy from empty space that GR says you will make a black hole. And this guy said, well, what's wrong with black holes? They exist, right? You said, well, yes, the existence of these black holes makes quantum mechanics non-predictive because they have singularities and infinities. End of story. You sound very clever, it's awesome, but this guy's going to tell you, I think I'm in the wrong. Thank you very much.
That's my prerogative, I can bend all the rules. And so my question is this, so there are a huge number of people who are building these theories that combine QM and GR. Are you telling me they're on the hiding to nothing?
No, it's okay. So what I did not say in the talk is that because I was trying to avoid complicated words, is that what we have actually done, successfully done, is to unify special relativity and quantum mechanics. And that theory is called quantum field theory. In fact, all these things that I told you, how to sum up all these diagrams and all these things, are actually rules of quantum field theory. And this is one of the great success of the 20th century, where people come out, spend 30, 40 years understanding how to sum up those terms, which is naively infinities. Those are really hard things to do. I mean, I sort of glossed over it. You can sum it up, but you can sum it up as actually a lot of work. And quantum field theory is the one that's incompatible with GR. The rules of adding those diagrams up to get you infinity is that's what breaks. And let's say string theory is a way to replace the quantum field theoretical rules with some new rules, which is called string theory. And let's say loop quantum gravity is something that is a set of ideas that says that, well, you want to, space-time is not really continuous like GR predicted by some chunks of this quanta. So all these ideas that people are working on trying to unify quantum mechanics and GR is in a way trying to break some of the rules, but it's very hard to break some of the rules. They're also well tested experimentally. So I guess to answer your question, a lot of people are working on these things, and string theory, look on gravity, on the other, and modify gravity theories. All this are like trying to find like loopholes in all these little rules that we have to try to unify the two theories.
Okay. So we might get a T-shirt after all.
We might get a T-shirt, yeah, but you just tell the government to fund more research.
Thanks, T-shirt.